So I would like to thank the organizers for putting together this fantastic conference. So I already learned a lot. So today I would like to ask a very simple and basic question. I'm only going to report about a single series of experiments that we did. And it's the question, why does sometimes the same physical stimulus reaches a stage where it can be reported, whereas at some other times the very same stimulus may not reach that critical stage? Okay, so that's the question. And then, of course, if a stimulus fails to reach that stage, one can ask, what then happens? What goes wrong? How can it be lost? So in my talk, I'll be mainly talking about reports, say access consciousness. I won't be saying a lot about phenomenal consciousness, but I actually think that the data that we obtain here gives also quite strong constraints for theories of phenomenal awareness. So I will start to do this very simple experiment with you. So I'm going to present a stimulus. So if you see the stimulus, please raise your hand. If you don't, well, don't raise your hand, okay? Are you ready for this? 1, 2, 3. Okay, that was easy. Now I'm going to make it more difficult for the good observers. So 1, 2, 3. I see a few hands, okay? Let's try it, make it more easy again. 1, 2, 3. Yeah. And the last time. 1, 2, 3. Nobody saw it. Well, that was true. There was nothing. Actually, there also was nothing on the second try. So those that kind of raised their hand, that was what we call a false alarm. And so this is very well described by the so-called signal detection theory, a very dominant and influential theory that was already phrased many, many years ago by psychologists. And it kind of functions as follows. If there is a stimulus, the theoreticians propose that there is sort of an internal representation of signal strength that varies across trials. That is this green distribution. Okay, so on a particular trial where you present the stimulus, you sample from this distribution. So you could get on a particular trial this internal representation of signal strength. And then, of course, you have to decide, am I going to say yes, am I going to raise my hands or not? And so according to the signal detection theory, there's a single threshold. And if the internal strength is higher than this threshold, you're going to say yes. So that's a hit. And sometimes, of course, because you're sampling from this distribution, it may happen that the internal representation of signal strength is below the threshold. So you're going to say no, even though there was a stimulus. That's going to be called a miss. Now, on the trials in which there is no stimulus, you basically get a similar distribution, but that's, of course, shifted to the left, and in the signal detection theory, it's centered at 0. And so typically, you would stay below the threshold, so that would be called a correct rejection. But occasionally, and that is what happened here, you can actually have an internal representation that crosses this threshold, and then you would say yes, even though there was no stimulus. That's called a false alarm. Okay, so, and of course, it's intriguing to think what is the best place for this threshold, given these two distributions. So if you have a signal that is a bit stronger, you get for the target present trials, you get a shift of the distribution to the right. And now with the same threshold, you actually get still quite a number of false alarms. So you might want to become a bit more conservative. Shift your threshold. You'll see that you don't get a lot of more misses because you're still kind of on the left side of the green distribution. So this is just a better threshold. Of course, now, if you would have a weaker stimulus, this threshold is clearly suboptimal because you would be missing a lot of stimuli. So this is basically the essence of signal detection theory, right? So there's a compromise that you have to make. How bad is it to make a false alarm? How bad is it to make a miss? And then you have to find a compromise that kind of gives the best ratio between misses and false alarms. Okay? So now, what is not addressed by the signal detection theory is the question of where is this signal, this internal representation of signal strength? Is it in a particular brain area? What is it? And second, something that's also interesting to think about is what causes this width of the distribution of internal representation of signal strength across trials. So that is what we set out to test. And to continue my introduction, there is a theory that is the global neuronal workspace theory that seems to give a bit of hints of how you might think about the signal detection theory, but then in neural terms. And so these are a couple of studies that made proposals in this direction. And the the essence of the scheme is as follows. So this is the LGN that presents or propagates information to primary visual cortex and then to higher visual areas. And in the global neural workspace theory, there is this sort of magic event called ignition that then causes it's thought to be due to reciprocal interactions between neurons, for instance, in frontal and parietal cortex, that causes a self-stabilized pattern of activity. And even if the stimulus is no longer there, it can be self-sustained. So in some sense, it's a memory trace of a stimulus that you just saw, allowing you to report it at a later point in time. Okay, so what then is the prediction is that if there is a stimulus and if it reaches awareness and can be reported, then you get this self-stabilized state, but sometimes it might not propagate strongly enough to the higher levels and it fails to kind of cause this ignition and it would then result in a miss. Okay, so that's what we set out to test. So we basically trained monkeys on this very similar test that you've been doing. So they will be looking at the fixation point, and on 50% of the trials we present a stimulus, and then after a delay the animal is supposed to make an eye movement to where we saw the stimulus. On 50% of trials there's no stimulus and there's always this small dot, we call it a reject dot, that allows the animal to report that he didn't see anything. Okay? So then of course you can vary the contrast of the stimulus. This is on the x-axis, and it's not very surprising. It has been shown many times that if you have a strong stimulus, the animal will basically always report it. And then you can decrease the contrast. The animal is basically on a staircase. And at some point, he reaches 80% correct. We call this the high threshold. And then if you reduce the contrast further, he can get 40% correct. So we also have a low threshold. So above the high threshold, we call the stimuli easy. Between the two thresholds, we call the stimuli of intermediate difficulty, and below the low threshold, we call the stimuli difficult. That's just kind of a convenience for the analysis of the data that we'll be doing later. Okay? So that's the idea, and then we record it from primary visual cortex, from area B4, which is a high visual area, and dorsolateral prefrontal cortex, where there are neurons that are actually involved in the generation of an eye movement towards the stimulus. So that's basically how we're going to read out the report. And now, when we started to do this experiment, the first surprise was, so what we're doing here is comparing precisely the same stimuli, precisely the same contrasts, but we compare trials in which the animal reported the stimulus to those where he failed to report it, where he had a miss. And you see already at the level of primary visual cortex, there's a difference. And this is very early on, from the start of the response, as if on some trials there was a failure of propagation from the retina to the level of primary visual cortex already, explaining some of the variance in the animal's report. And you see that this difference is also there, but you see that in proportion at least it becomes smaller if the stimulus was easy. And it's interesting to see that the missed trials with an easy stimulus actually elicited more activity than the hit trials with a difficult stimulus, suggesting that the level of activity in primary visual cortex is not fully predicting whether the animal will be able to report the stimulus or not. Okay? Now, so we can actually now quantify the miss fraction, which is the ratio between the missed trial, the activity on missed trials and hit trials. You see that it increases with difficulty. There's in proportion more activity on the easy trials. And we can do the same experiment in area V4. And basically we get the same effect. So maybe the difference between hit and misses is a bit larger on the difficult trials. So again, V4 is not categorically predicting where a stimulus will be able to be, where the animal will be able to report the stimulus or not. And then we record and the miss fraction increases, as you saw before. And then we record it in dorsolateral prefrontal cortex. So here we're kind of looking at the eye movement plan. And you see that now the difference, it's quite a big difference. Now it's more or less categorical. Whenever the animal reports the stimulus, you get a big response. And whenever the animal fails to report a stimulus, you get a much weaker response. But you see that even the strength of this response increases with the contrast. But it seems as if this, on the mistrials, it just is not strong enough for some reason, for some stochasticity. And this may be related to what Alain was talking about. Maybe the brain state is not permissive for the propagation of activity. Okay, so here you get a relatively constant miss fraction, and at this level you could put a threshold. So this is a candidate region that has this internal representation of signal strength, making the difference between whether something is going to be reported or not. Now we also record activity during those trials in which there was no stimulus, so we can compare the correct rejections to the false alarm trials, which is shown here. So the correct rejections are here in black, and you basically get a homogeneously small activity level. But on the false alarm trials, you get this apparent ramping of activity to the same level in dorsolateral prefrontal cortex that is reached by the HIT trials. So what's going on here? Well, we think actually that there's something going on here that we call spontaneous ignitions that can happen at different time points. So due to the stochasticity of the signal, the activity might reach this level where it can self-sustain itself. It happens only on maybe 5% of all the trials, but that can happen, of course, at different time points. Actually, on the trials without a stimulus, there is not a natural time zero, which is the time where we would have presented the stimulus had we presented the stimulus, but we did not, right? So if these spontaneous ignitions happen at different time points, then if you average across trials, you see this ramping of activity. Okay, so this is fairly consistent then that dorsolateral prefrontal cortex could be one of the regions that has this internal representation of signal strength, because you see that the false alarms and the hits have more activity than the misses and the correct rejections. Okay, so now the question is, where then does this stochasticity come from? Why does the same stimulus sometimes reach a strong enough response in frontal cortex, and why does it sometimes does not reach that level? So previous studies have also looked at that. We were interested in whether we can predict the outcome of a trial based on the pre-stimulus brain state. Again, much related to what Alain was talking about. And this is what Catherine Talon-Baudry also talked about yesterday. So in the signal detection theory, there are two interesting parameters. First is called the bias. That's the bias, the propensity of the animal to say, yes, I saw something. So if you have a high threshold, the animal is conservative. So he will have quite a number of misses, which is the area under this green curve to the left of the threshold. And you can basically have less of these misses by shifting the threshold to the left. But of course, this will now go at the expense of having more false alarms. Okay, that's the bias. Now the other parameter is sensitivity. And that is actually related to the distance between those two distributions. So if you have a threshold here, and if you would be able to somehow propagate the information more efficiently to those higher levels that are going to decide whether it's above the threshold or not, then of course you can actually have an increase in the number of hits, but without an accompanying change in the number of, or the proportion of false alarms. Okay, so that's measured in the signal detection theory as the d prime, which is the distance between those two distributions. Okay? So basically what we then did is looked at several pre-stimulus markers of brain state, and the first measure is quite intuitive. So the animal starts a trial, we present a fixation point, and then the animal starts a trial by moving his gaze to the fixation point. And sometimes he's quite kind of motivated as quickly, sometimes he's not so motivated anymore, so it takes a long time for him to attain fixation. So we can see whether the time to fixation predicts whether the animal is going to have, for instance, a hit or a miss. And we quantify the effect as the area under the ROC curve. Now, if the animal is not very motivated, it will take a long time for him to attain fixation. It actually reduces the number of hits. So therefore, you get a value of this ROC, this area under the ROC curve that is below 0.5. 0.5 would be chance level. So there is some predictive power in predicting the probability the animal will have a hit based on the time that it takes him to attain fixation. Okay? You can do the same thing for the pupil diameter or the first derivative of it. Many studies have been published on this. We don't see very strong relationships there. You can look at the pre-stimulus multi-unit level, so the spiking level before the stimulus appears. This is in V1. You see there's a little bit of predictive power. You can look at the different frequency bands of the EEG, so we do alpha, beta, gamma, low and gamma high. So you see there are some subtle effects. Many papers have been written about it. It's not all that overwhelming, I must say. Now, the next step then is that we did is you have all these 8 markers of pre-stimulus brain state. Maybe we can combine them. Maybe we can linear combine them to get a better prediction. So this is what we did. And this is the joint. And then you see you start to do a little bit better. Now we can predict the outcome of a trial with 60% accuracy, where 50% will be chance level. It's not overwhelming, but it's probably one of the best that has been done. Okay, so you can play the same trick then by those trials without a stimulus, predicting whether it's a false alarm or a correct rejection. You get a slightly different profile, but overall, if you you make a joint measure, you see you have a similar degree of performance. And you can play the same game with the data from V4 and dorsolateral prefrontal cortex, and you get fairly similar results. Okay? So now back then to this idea about the bias. So we are now trying to predict the bias using a joint measure of a number of pre-stimulus brain state markers. The bias is basically, if you look at the false alarm, or the trials without a stimulus, the probability that there will be a false alarm, right? It's the location of this threshold. And so now we can see how good we are in predicting the bias. So what we did here is we sorted all trials based on this joint pre-stimulus brain state marker called B for bias. And you see this is when the stimulus was easy, the animal is almost always correct, and here is no stimulus. So you see this is an increase in the number of false alarms. I mean, this is how we defined the B. But now it's interesting because we now can go back to the brain and see how these trials, this pre-stimulus brain state that makes the animal likely to commit a false alarm, how that affects the neural activity. And basically what we find is kind of intriguing. You see that, for instance, in dorsolateral prefrontal cortex, if the bias is high, there's a high level of spontaneous activity, as if these neurons are already relatively close to the threshold for ignition, right? Therefore, explaining why there's a high probability of committing a false alarm. And you see similar effects in V4 and a little bit in area V1. Okay? Now the other measure is sensitivity. So now we're trying, based on this conjoint measure of 8 pre-stimulus brain state markers, to make a measure that predicts that there's an increased probability of a hit, but we don't want to increase the number of false alarms. So it's possible to do that. And you see this is then the influence of this measure S on the accuracy of the monkey, and you see you indeed get an increase in the hits without an increase in the number of false alarms. So we are able to do that, and it's interesting then to look how this affects then the neural activity, which is shown here. And you basically see that on those trials with a high sensitivity, you indeed get a better propagation of the information through the system to the higher cortical levels. This is very visible in dorsolateral prefrontal cortex, but it's also visible in area V4, and there's a trend in the same direction in area V1. Okay? So to summarize this, so if this is the standard situation, on those trials with a high B, actually what you see is that 2 distributions basically shift to the right. There's a higher spontaneous activity. So it's not the threshold that shifts, it's actually the pre-stimulus activity that shifts to the right. Of course, this has the same effect as lowering the threshold. And you see that for high sensitivity trials, there's a better propagation of activity to higher cortical levels, and therefore you get a more cleaner separation of the 2 distributions at the level where it really matters. Okay? So now there are many ways for a stimulus to reach an area in the cortex. And only some of those use cortical-cortical pathways. So we wanted to know whether stimulus propagation along cortical-cortical pathways indeed contributes to this variability. So we did a very simple experiment. We just replaced the visual stimulus by direct activation of a group of neurons in primary visual cortex with microstimulation. Then the animal is going to perceive a phosphene, a dot of light that is not really there. And then we're going to record from area V4 to see how well this information from V1 propagates to area V4. Okay, so the paradigm is very similar, but there's no visual stimulus now. We just replaced it by an electrical stimulus. And we get well-behaved psychometrical functions, so we can basically play all the same tricks. And this shows you, this is of course of some importance, so this is this receptive field of those V1 neurons that we're stimulating, and V4 has larger receptive fields. This is shown here in false color, and we always looked for cases where the V1 and the V4 receptive fields would be overlapping. And this shows you when you present a train of 5 microstimulation pulses, total duration is 20 milliseconds, on individual trials for a stimulus train that is clearly above the threshold, and you see, basically on every trial, you see an elicited activity in area V4. That basically looks a lot like if you present a visual stimulus. Okay? So now we can sort then those trials where the animal perceives it and where he doesn't, and this is when we give only a little bit of current, this is when we give more current, and this is where we give a lot of current, and you see particularly for those trials where we give little current, there's a large difference in the degree in which the activity propagates from V1 to V4. Okay? So yes, there is actually variability in cortical-cortical propagation that may contribute to the width of these distributions. And it's also interesting to see that we replicate here the fact that The easy miss trials elicit more activity in V4 than the difficult hit trials, again suggesting that there can be loss of information downstream from area V4. And this is then quantified as an increasing miss fraction. Okay, so a couple of years ago when we were working on this project, I talked to Stan de Hane about our results, and he got really excited, and he says, oh, I can model that, and he had several models already published, but then he kind of took the endeavor to really simplify his model to the bare minimum. And this is the model, and actually it's only 5 stochastic neurons, so the whole brain is now modeled by 5 stochastic neurons, okay? So LGN, the activity starts here, it propagates to higher visual areas. You have feed-forward connections here in the model, feedback connections and self-connections. And the feed-forward and feedback connections are a bit stronger in the parietal and frontal cortex. And therefore the activity there can be self-sustained. So even if the stimulus is no longer there, it can uphold its own activity. And if that happens, if you then take away the stimulus, the activity can stay, and that would be a hit trial. Now, due to the stochasticity, if you propagate the information on another trial for the same stimulus, maybe it just stays below the level of activity that is needed to switch to this self-sustained state. Okay, if that doesn't happen, activity collapses again, and that would be a mistrial in the model. Okay? Now this shows you the data from the model, and basically you see that you get more activity on hit trials than on mistrials in area V1, an increasing miss fraction. The same in V4, and you get a more categorical representation of whether the animal is going to report the stimulus or not in the frontal cortex, because this is part of the set of regions that can sustain the activity for a later report. Okay? Now you can also, so you get kind of a constant miss fraction. You can also look at the trials with false alarms and correct rejections, and here we can be really sure about what's going on. If you look in the model, you see these spontaneous ignitions that can happen on a very small fraction of trials, but if they happen at an unpredictable time, and again, time 0 is not really well defined for those trials without a stimulus, and therefore, if you average across trials, you get this ramping of activity, just as we saw in the neurophysiological data. Okay, so this is the data from the model. And this is the data that we painstakingly recorded, and thought it was a bit embarrassing. So we spent a lot of time here, and this could be done within a single day. Okay, and you see how much actually of the activity you can explain with a single model with only 5 neurons. Now, fortunately, the brain has different tasks than contrast detection, so probably there's a role for all these other neurons. But so I was really intrigued by how well this model describes the data. Okay, so I'd like to phrase my conclusions. So we see that weaker stimuli tend to get lost at lower hierarchical levels than stronger stimuli. We see that false alarms can be explained by these spontaneous ignitions. We see that behavioral and neuronal markers of pre-stimulus brain state can predict parameters of the signal detection theory, bias, and sensitivity separately. And I would claim that the global workspace theory gives an excellent account of how a weak visual stimulus may not be reported as a measure of access awareness. So these are the people who did the work. So Bram van Vught, Bruno Dagnino, and Dev Vartak were involved in the recordings. Hauman Savai and Stefano Panzeri defined those measures based on a combination of pre-stimulus brain state markers, and Stan de Hane did a lot of the modeling. Thank you very much.
Thank you. There's a couple of questions here. Yeah, please go ahead now. Microphone. If you have the microphone. Well, okay. Please start.
Can I ask a question? Or?
Yes, please go ahead.
Yeah, thanks. It was really a really cool talk, really cool data. But I was just to put maybe a critical question. Isn't it pretty sure that what you're showing is not a correlate of consciousness, because your visual experience is really short? I think you presented that really shortly. but the sustained activity goes on. So this sustained activity is necessarily not a correlate of your visual experience, but indeed of memory or preparation to make an eye movement, right? Would you agree with that?
So what we are using here is the possibility of the animal to report a stimulus, right? So in many theories, you would first have a stage of phenomenal awareness, and then that needs to be read out to be reported. That's typically called access awareness. And so I think what we have here is a clear correlate of this report. And I think it strongly constrains theories of phenomenal awareness, but I agree with you that we did not really target that. There are some practical issues that it's somewhat more difficult to get at the neural correlates of phenomenal awareness in monkeys, although there are now studies that are able to do that, for instance, using rivalry paradigms. So I think what I would be looking for if I wanted to continue this study and look for a neural correlate of phenomenal awareness, I would like to use one of these no-report paradigms. And I would strongly suspect that there are other areas that might have a similar sort of bifurcation that goes to a report state or a no-report state, and that would then need to be measured in a situation where the animal is not asked to report his percept on every trial. But again, that also makes the analysis more difficult, right? Because we can now use on every trial the outcome, and we know whether the animal saw it or not, right? So in that sense, yeah, you make your life more difficult if you want to use a no-report paradigm.
All right, now first, then Paul.
Cyril wants the guy to go first.
Actually, Peter, so you already said 1/3 of what I was going to ask, so no report paradigm. But I think your monkey is already almost ready to go to the no report paradigm. The psychometric function you showed in the beginning seems to show that you have lots of room to go into the much higher contrast stimulus. And what I suggest is not to put the stimulus in a really short duration, like Yara actually pointed out, but present it a long duration, and then ask monkey actively to ignore them. And then that's really, actually done in the human fMRI already, and that kind of fMRI study already shows a strong inhibition in prefrontal. So I think that's already almost possible to do.
So I think you're also alluding to another debate that's going on about the role of the frontal cortex. So in some of the no-report paradigms, during binocular rivalry, for instance, you actually do see strong neural correlates of whether something is in phenomenal awareness or not, also in frontal cortex. But I agree with you to change, we would need to change the paradigm to also make a similar measurement in a no-report paradigm. And that's something that we are actually actively thinking about. And there might be interesting new ways to try that out. And I think that would be a really exciting experiment.
Okay, thank you, Paul.
Yeah, so Peter, great work, thank you. But so you set out to test the global workspace theory, but have you not invalidated it actually with your result? Because you rely very much on your dorsolateral prefrontal cortical response, which is more categorical, which you might interpret as something like an ignition type signal, which would then allow information to enter the so-called global workspace. But now there are two problems. On the one hand, you have not really measured over any area in between, so you don't really know about the continuous information transfer. And secondly, the so-called cognition you see is also very close to your frontal eye field. So maybe it's much more an action-related signal that just drives the frontal eye field for the eye movement than that it is telling us anything about the content of the mental process in between.
So it's related to the previous questions. So I do not agree that we are just recording a simple motor output, because actually you see the ramp of activity that precedes and that integrates and that maintains a trace of the stimulus. Now, I agree with you, it would also be interesting to record in other areas. And for instance, what also would be interesting is to also use different response modes, for instance, a lever release or another way of responding. Because then I could imagine that there are areas that contain the trace of the stimulus that are response modality independent. Now we are close to the frontal eye field, so in our case, we are probably recording many neurons that are related to the intention to move the eyes. It would be interesting to see whether there are brain regions where there is kind of a more modality independent intention to report the stimulus. And of course, and then we go back to the next step, it would also be interesting, as I just said, to do something similar in a no-report paradigm. So this is still some kind of very interesting experiments to do, but I think we have now a really nice framework in which we can start to address these questions.
No, but the challenge is a bit a different one, right? Because you emphasize continuous integration that you see dorsolateral prefrontal cortex, but if you speak of something like ignition, it's a much more transient kind of change to the signal than what you report.
No, I don't agree to that. So what the ignition is not a transient event, it's the transition from something that can still be kind of become unstable and does not give rise to a working memory trace, or something that reaches a certain threshold and then gives rise to a working memory trace. But you want this working memory trace to be maintained so that a trace of the stimulus or the stimulus can be reported at a later point in time when it's no longer there.
All right, brief last question, please. Here.
Very brief question. A lot of questions already been asked. It's a very nice study, but I just don't want to ask which of these results do you think is most surprising to you?
Yes.
Because a lot of this is expected, I would think, right?
Yes, so what was surprising was the fact that you already see a difference between stimuli that are going to make it and those that are not at the level of primary visual cortex. It was surprising that you can actually use a combination of pre-stimulus brain state markers to separately predict where the bias of the monkey is going to be, or the sensitivity of the monkey is going to be. And I think it's very surprising that with a model of only 5 neurons, you can account so much of this data.